Okay, so this is week 7, and I would like to talk about two discrete symmetries, parity symmetry and time reversal. So as usual, feel free to stop me whenever you want. Just unmute yourself and speak, ask your questions. Right. Okay, so let's talk about first parity symmetry. Let's use this pi. And one important property we need to know is the parity is it's like a both unitary and also Hermitian, right? Unitary means pi dagger equal to pi dagger pi equal to 1, right? Hermitian means pi equal to pi dagger. Or together you can write in this form. So in classical physics, the space we care about is the phase space, right? It's x and p. So x transform to minus x, p transform to minus p under the parity operation. So we want to somehow preserve this nice property in the quantum mechanics. So we require this kind of oops, similar properties. I'm pretty sure you know this. I just want to very briefly summarize all this kind of stuff. Okay, so in the quantum mechanics, there's another degrees freedom, which is very important, which is the spin degrees freedom. Of course, from the algebra point of view, the spin is the same as the orbital momentum. So we know the orbital momentum is x cross p, and so it's even under the parity.
By the way, what do you mean by phase of x and p?
Sorry, phase space, right?
Uh,
Yeah, it's like a space for classical mechanics, right?
mm-hmm.
Yeah. By the way, there's another important point is the pi square equal to 1, meaning that the eigenvalue must be plus 1 minus 1. What else I want to say about this? Right, okay, so this kind of a parity operation preserves the basic commutation relation, right? So you can say xp equal to I h bar. If you apply the parity operation, you still get this. Similarly, for the spin algebra, you still get the same spin algebra. Okay, so another thing I want to say is okay, this is the first stuff. The second stuff is what we you're gonna say is parity state. So basically, if we act a parity operator on some state, then if we get plus or minus the state cat, the cat alpha. So if it's a plus sign, we say it's a even parity state. If it's a minus sign, it's an odd parity state. Of course, you can represent this relation in the real space, right? You just need to, this plus minus x alpha. So this guy is nothing but this. And this would tell us psi alpha minus x equal to plus minus psi alpha x. So the even parity state and odd parity state corresponding to the even function or odd function of your wave function. It's very, very obvious, I would say. And another thing is this parity state, this parity operation together with the identity operator form a Z2 group, right? So with this relation. This is a Z2. For this kind of odd parity state, recall if it's an odd parity state, let's say alpha, this is a one-dimensional space. This space is a representation space for this parity operation, this Z2 group, and it's a non-trivial. Trivial representation because in this space, your Z2 originally is identity pi, represent using numbers because it's a one dimension. So every element is a one by one matrix. One by one and matrix is nothing but a number. So identity is one, and pi becomes minus one, right? Because pi acting on this guy give us a minus. And even parity state is also a one-dimensional representation space for this Z2 group, but it's a trivial representation. As you can see, this pi acting on the state alpha trivially is a 1, right? So this guy map to 1, 1. All the elements in the group map to identity, so it's kind of trivial. Any question about this part? Okay. So what's the next thing I want to see? Okay, so another thing is if this Hamiltonian has the parity symmetry, so what we can see about this Hamiltonian, about this system. So I'm pretty sure you know that if there's a non-degeneracy for some energy levels n, then this state n must be even or odd, right? This is also quite easy to prove, like h n equals some this guy, you act by definition is eigenstate, you act your like a parity operation on this equation and the commute. So you get this, meaning that uh, this pi acting on your state n is also an eigenstate of your system, but we know there's no degeneracy for this eigenenergy, so there's a only a phase difference between this state and this state. And on the other hand, we know this pi can have has only eigenvalue plus or minus one, so it's like this. Okay, so basically it's saying that the non if your eigencat, if that eigenlevel is non-degenerate, then it's form a irreducible representation for a Z2 group, right? If it's all if this cat n is a odd parity state, then it's form this kind of non-trivial representation. If it's even parity, then it's just a trivial representation. Similarly, you can apply this kind of a discussion to the degenerate case. In this case, um, generally speaking, okay, so let's say your H acting on some Ni equal to epsilon, so energy N, um, and your state I is 1 to N. So the degeneracy is N, and the pi acting on this guy is also an eigenstate with energy En, right? Same argument we applied here. But in this case, what we can say is this is a linear superposition of all the other states in this degenerate space. And we know from this equation, we can find the elements. So in this case, your pi, your parity operation is like a m by m matrix, right? And of course, it's a unitary and Hermitian matrix. Okay, in this case, we cannot say this guy is a parity state, even parity or odd parity, right? Because such an argument that there's only a phase difference cannot apply in this case. It's non-degenerate. But the point is, by diagonalizing this matrix in this degenerate space, we can always find a basis such that the basis are odd or even parity, because we can always diagonalize this operator pi in this subspace, so in this degenerate space. And this is equivalent to find the irreducible representation of this Z2 group. Yeah, this can be diagonalized into this kind of a form. In this new basis, the base cat will be even or odd parity state. Is it clear what I'm saying here? Okay, maybe I can give you an example, a very simple example. You will see explicitly what I'm saying here. So let's say I have a potential infinite deep well, and this is x equal to 0. if we look at the ground state, by the way, this Hamiltonian is like this. Definitely, it has this symmetry parity in is invariant under parity operation. Now we know there at the ground state.
But
Question? Okay, so we know in this case the ground state has two-fold degeneracy, right?
the angular momentum is always going to be 0.
What's that? Okay, right. Okay, so this is the ground state. Let's denote this guy as
Now let us consider the position and velocity of the particle at the instant t.
okay.
Right, the two vectors r and v lie.
Okay. I think I just forgot to mute and so yeah, whatever. Yeah, let's denote this ground state as L, this state as R. Definitely this L and R, of course you can write them in some real space representation, right? It's kind of a sign function, but the argument somehow, yeah, you can write it down by yourself. Okay, so yeah, in this basis, you can say this pi acting on L is R, and the pi acting on R is L. So they are not both of them so they are not parity states, right? But in this basis, we can write down this pi, which is 1, 1, I'm pretty sure. Yeah, in this basis. By the way, because this kind of a pi parity operator, pi, is both unitary and Hermitian. Remember our Pauli matrices is also unitary Hermitian, right? In many cases, it just breaks down to some, this is nothing but sigma x, right? Okay, so yeah, so in this basis, the cat is the cats are not parity states, but by diagonalizing this guy, we know this guy has eigenvalue +1 and -1. It's easy to calculate. And in this new basis, the basis is, you can say the cat, sorry, the eigenvector is kind of a 1, 1 and 1 - 1, right? So in the new basis is written in this way, L plus R, L minus R. So you can see in this new basis is just it's a parity state. This is even parity, this is odd parity. Yeah.
What is some of the practical benefits of finding the parity eigenstates? And does it help us perform measurements or something?
I mean, you always want to kind of classify your states with some quantum numbers, right? This is serve as like a quantum number to, yeah, to kind of classify your states, separate your states.
So in this sense, there's like nothing special about the fact that this is a parity operator, just the sum operator that commute with your Hamiltonian, so you can use it to break the degeneracy of sums of space, right?
Right. Yeah, this is the whenever you say okay, the ground state, sorry, the Hamiltonian commute with the parity operator, you can always do this kind of analysis, separate all the eigenstate into two parts, and one is odd and one is even though it's kind of a degenerate. You can always do some superposition like what we did here to make them even or odd. Okay, so let's give you guys more examples, which I'm pretty sure you're familiar with. First one is the harmonic oscillator. Right. Yeah, the potential looks like this. It's also kind of a symmetric around the y-axis. So it's also commute. This guy was commute with our parity operation. And from the standard, it's kind of a procedure. The eigencat for the eigen levels, there's no degeneracy, meaning that we don't need to do this kind of a diagonalization procedure. For each state, there must be odd or even state. So for the cat 0, the ground state, we know it looks like this. It's a even parity state, and this guy is given by a dagger 0. A dagger is some linear combination of x and p. X and p will flip the sign on the parity, meaning that this guy would also flip the sign on the parity. So this guy is the odd state, and this yeah, this one state 1 according to the definition look like this. Like this, I just insert this guy. So this is minus a dagger because a dagger is linear in x and p. And pi acting on 0 is 0 itself. And this guy is 1. So there's a minus sign. So you can apply this this kind of a procedure to the general cat n. You would get this.
Is there a good way of knowing, maybe you covered this and I just forgot it. Is there a good way of knowing without actually solving the differential equation that 0 is an even parity state? Is that generally true?
Yeah. I guess for most of the kind of a convention potential, not some exotic potential, it always true. Yeah. Because the ground state always want to avoid some kind of a sharp change in your wave function, because there's a p squared over m. It's kind of a spatial derivative. You always want to be smooth, right? If it's all the parity, you always get something like this. But for the even parity, it's like the ground state I'm talking about. It's more smooth compared with this. It's like yeah, it's very hand waving, but it's convincing, at least to me. You can think about also this kind of example. Something like this. Yeah, whenever you have for this double well problem, if there's some yeah, this is also kind of classical, very classical examples. Whenever originally it's kind of a two degenerate has two degenerate space, but when if assume there's some finite potential, meaning that you can tunnel in between those two wells, then it will hybridize and get a symmetrized and anti-symmetrized state, and the degeneracy will no longer there. And in this case, you always get a ground state like this, and the symmetry state is a ground state, and the anti-symmetry state is the first excited state. And yeah, because your wave function always want to be smooth enough to minimize your this guy.
So, and if you have a Hamiltonian that does not commute with parity, does that tell you something about its eigenfunctions? Would that mean that they like have to be neither even nor odd or something?
Maybe some of them can be a parity state, but I'm pretty sure not all of them. Wait,
Or is that even something that's physically relevant? Meaning like, you know, in your research, do you need Hamiltonian that are not commuting with parity?
Which really, okay, so whenever we care about some symmetries, it's because the symmetry is kind of is a symmetry in my problem, right? And it can tell us something from the from the fact it's a symmetry. If it's not a symmetry, I mean, generally speaking, it's unclear, I guess. But like what you said, for this parity symmetry, which is very, very special and very simple, because the corresponding group is just a Z2. The only kind of a non-trivial operator in this group is this parity operation, unlike other Lie groups like continuous symmetries. Yeah, like intuitively, it seems tells us all the eigenstates, like what you said, must be not even or also not odd. But I'm not sure. I need to think more about it. You can also check by yourself, I guess. Okay, so this is one example. Another example definitely should be, so this is like in somehow in the real space. Okay, so another example is related to the spin algebra. So I would say this is also parity is also a symmetry in this problem, right? It's like you have some particle moving in some spherical potential and apply some magnetic field along some direction. Then you get this Hamiltonian. In this case, you know, the Hamiltonian, the energy can be labeled by L and M. L plus 1 plus M, something like this. And there's no degeneracy, meaning that the eigenstate must be odd parity state. This is also easy to see. For example, for L equals 0, M equals 0, basically corresponding to the S orbital, S wave. in this case, it's a spherical symmetric wave function. Okay. Because the y 0 is just a constant, meaning that in each direction the wave function is the same. Definitely this corresponding to a even parity state. And if you look at this guy, m equal to 0 and L is L, there are some coefficients, constant coefficients. Okay, I guess I can write it down because m equal to 0 is quite simple. PL cosine theta. And if you apply this kind of parity operation, this the cosine theta becomes cosine pi minus theta, which is minus cosine theta. Remember this guy minus x equal to L. Just the property of this special function. So this guy, the parity operation flips the sign of this cosine theta. So similarly, it will flip the sign of this guy. So it's a pi acting on this guy would give us this. So L equal to 0 is even parity state. L equal to 1 is what it's even it's an odd parity state. I'm pretty sure you can also look up on the shape of the wave function. You get some idea, like the pictures. So this L0 has the same parity property with the LM, right? Because LM can be obtained by acting this kind of L plus L minus on this L0. And this L plus will not change the parity property of your state because the L plus is Lx plus I Ly. They are both even they both commute with the parity state. It's a parity operation. So generally speaking, you can change this at 0 to m. Yeah, any question about this part? Yeah, here are just some basics properties about the parity. It's a quite important symmetry. We need to be care about. Yeah, it's like in the field theory, like besides this kind of continuous symmetry, like Lorentz symmetry, whatever, there are like three important symmetries, like CPP, right? In condensed matter, similarly, except there are also some important discrete symmetries we care about, like a parity time reversal particle Hall symmetry. Yeah. This is one of them. Yeah. So it's some basic properties, and also some consequence of this guy and some examples. Very familiar examples. Yeah. Okay, so let's talk about time reversal. So time reversal is very special because it's a anti-linear. I think this is the only anti-unitary. This is the only anti-unitary operator. Because like what we discussed a long time ago, we usually realize the operator on operation using the unitary operator, right? Acting on some Hilbert space we care about. But it turns out time reversal is quite special. It must be realized by some anti-unitary. And I'm pretty sure you know the definition. It's like C1 some cat A plus C2 some cat B. We will get C star this. We can write this kind of operators into the product too. This guy is complex conjugate. This guy is a unitary operator. Similarly, we can define the properties of some operators under the time reversal operation. So also inspired by the time reversal in the classical physics, we would require this X to be invariant under the time reversal, and also the P operator flip the sign because the motion of the direction of the motion will flip, and also the operator J, we want to flip the sign because J is not X plus P. And another another special thing is if whenever you have a complex number, you always want to take the complex conjugate of this number. It's due to the fact that time reversal is an anti-unitary operator. So combined with all these properties, we can say that this time reversal also preserves the basic commutation relation. This is for XP, and another one is for the spin. We always want to preserve this kind of fundamental properties, right? You can add your operators onto two sides of these two equations, and you get the same equation. Yeah. And you can also see a lot of stuff from this kind of basic commutation relation. For example, from this fact, we can say, okay, the time reversal actually commute with the translation, right? Because the translation can be written as minus IPA. And whenever you act your time reversal on some operator, your I flip the sign, but the P also flip the sign. Similarly, from this guy, we would have, it's also commute with rotation. Let's denote as this. This guy can be written as exponential minus I J dot N phi. So the I flip the sign, the J also flip the sign. Okay, so these are just some properties, the basic properties of time reversal. I just copy from the textbook, and yeah. I guess you need to know this. It's also easy to remember, right? It's just some classical generalization. And similarly, we would ask, what's the consequence of this guy? What if my Hamiltonian commute with the time reversal operator? If there's non-degeneracy, the consequence is the eigencat always real. Of course, if n is your eigencat, then the time reversal of this cat is also eigencat. But so okay, means that this guy equal to this guy up to some phase factor. That phase factor is unimportant if you only care about this state, right? Or that phase factor is arbitrary. It's a constant phase factor. And if you write this guy in the x representation, this is psi x. This according to the definition is this. Yeah, because it's like x, 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 n, x, x, x. This guy acting here will get the complex conjugate. Yeah. This means your eigencat must be real. You can also look at some examples. For example, the same example, the harmonic oscillator. You can say, of course, this guy commute with the time reversal. By the way, usually we break the time reversal by applying some magnetic field or something related to mechanization. This guy, there's no magnetic field, or yeah, it's just some constant potential. Sorry, not constant potential. It's, yeah, x squared potential, and yeah, it's commute with the time reversal. If you remember, the ground state is something. Oops. Some constant in front, some exponential like this. There's some constant here. It's a real function. Of course, you can say, okay, there's some constant phase factor, but it's really doesn't matter. Right? And another example is, by the way, there's no degeneracy for this problem. Another example is h equal to p squared divided by 2m, the free particle. And in this case, if p not equal to 0, by the way, in this case, the eigencat is just the plane wave. Right? If p is not equal to 0, there is a degeneracy, right? It's p and minus p. So in this case, you can say this guy is non-zero. Sorry, it's complex in general. It's a real number only when p equals 0. P equals 0, your state is a constant, real constant. Because at p equals 0 at this point, there's no degeneracy. So it's a real constant. For p not equal to 0, there's a degeneracy, and it's kind of a twofold. And those two states are related by the time reversal operator. This is cat p. Then if you apply the time reversal, you would get this cat minus p. Right? Because this time reversal is like take a complex conjugate. You get a minus sign. Any question about this part? Okay, so the last example is, of course, again, this guy. Here we need LD square to make sure this Hamiltonian commute with the time reversal. If it's LZ, then it's not commute, right? If it's LZ, you can think of this LZ comes from the LZ dot B, dot the external magnetic field, which will break the time reversal. And also, you know, this LZ would flip the sign under the time reversal. So we want LZ square. Then this is the L plus 1 plus M square. The eigencat is LM. You'll notice that there's a degeneracy, which is LM and L minus M. And they were also related by the time reversal operator. Yeah, so if you apply a time reversal operator, generally speaking, you would get this. And you can check by looking at this expression of this spherical harmonics. Indeed, if you apply a time reversal, you would get this minus 1. And of course, when M equal to 0, there's no degeneracy because, there's no degeneracy. And L0, this guy is a real function. If you look up on the kind of the table for the spherical harmonics, this is real.
So should that pi be theta?
Where pi? Right. It's not parity operation. It's the time reversal. Thanks. Yeah, that's, of course, okay, there's for the if there's a spin degrees freedom, you can write down the explicit expression for the time reversal operator, and also there are some discussions on the Kramer degeneracy. I'm pretty sure Yaroslav mentioned that in the class, right? That's very important. And I don't think I have time to do that, so I will stop here. And if you have any questions, just feel free to just stay here and discuss with me. Otherwise, you're free to go.